Hello students, in today's lecture we are going to discuss the magnetic force on a current carrying conductor. So as we know that an electric motor has many charges and that does work. So what makes an electric motor work, and similarly how a moving galvanometer detects current. So from this topic we will explain that how an electric motor works and similarly how a moving galvanometer detects currents. So we can compute the force on a current carrying conductor starting with the magnetic force F equals to QV cross B on a single moving charge. As we discussed it in our previous lecture, that the force on a single positive charge placed in moving in with velocity v in uniform magnetic field, then the total force is given by this expression. So here we consider a conductor which has a length L and cross-sectional area A, and if we assume that there is a positive charge Q inside the conductor and which is moving with velocity v in upward direction, so it has a drift velocity v in upward direction. So the force on this which is, and remember that there is a uniform magnetic field B which is directed inward or into the plane of the diagram, and then the total force on this charge will be F equals to QVB, and it is by right hand rule we can determine the direction of this force, which comes to be towards the left as shown in the figure. So here we assume that V and B, the magnetic field, has an angle 90 degree. So far when the angle is 90 degree, then the force will be F equals to QVB. So we can derive the expression for the total force, as the conductor has many charges, and therefore we can calculate the total force on the conductor or for all the charges. So in this situation we have a conductor which has a length L and it has a cross-sectional area A. Then the number of charges in a unit volume is N, and it has a segment of the conductor which has a length L, and so its volume will be AL. So the total number of charges in a unit volume will be NAL. So the force on all the moving charges inside this segment is given by this expression, which is NALQVB. Here N is the number of charges, A is the cross-sectional area, and L is the length of the conductor. Q is the charge, VD is the drift velocity, and B is uniform magnetic field. Then this NQVD, these three things, this is called the current density, and when this is multiplied with the cross-sectional area, then it gives us the total current. So this term, which is enclosed in the parentheses, is actually the total current in the conductor. So the total force on a current carrying conductor which is placed in uniform magnetic field B is ILB. So if the field is not perpendicular, then let's say the conductor makes an angle phi with the magnetic field, then to calculate the total force on the conductor, then the effective component of the magnetic field will be the perpendicular component, which is the sign component of the magnetic field. So that will cause the force on the conductor. So this is the effective component which causes the force on the conductor, which is B sine phi. If the magnetic field and the conductor are not at the right angle, so the total force on the conductor will be IL, and the perpendicular component of the magnetic field, which is ILB sine phi. And remember, this force will always be perpendicular to both the conductor and the magnetic field. And we can calculate this force by the right hand rule as shown in this figure. If we stretch our fingers in the direction of the current and then we curl them towards the magnetic field, then the outward extended thumb of our right hand will determine the direction of the force. So this will be the force on the conductor, which is at some angle phi with the magnetic field. So we can also write this expression in the form of vector product, which will be F equals to I into L cross B. Here L and B are vectors, and the direction of L will be along the direction of current. So here in these figures there are several situations given where the direction of the magnetic field are different and length of the conductor similarly, the force will be different in each situation. So, and whenever the conductor is not straight, then for that purpose we will have to divide the conductor into very small segments, each one having length dl, and then for that segment we will determine the force dF on each segment, which will be dF equals to I dl into cross B. And then the total force on the conductor, we should integrate this expression with respect to L, and of course that integral will be a line integral. So here in the beginning we assume that and the conductor has positive charges. So what happens when the conductor has negative charges, such as electrons in the metal? So here in our situation the positive charges were moving in upward direction. So when the charge is negative, then the direction of current will be downward, and so the charge is now negative, then the force will be the same as for positive charges. So these equations, the equation number 27.20 and 27.17, these both equations are valid for both positive charges and negative charges. And this is true when, as in semiconductor materials, there are positive holes and negative electrons. Whenever that has some current I, and which is kept in magnetic field, then the direction of the force on the semiconductor material will be the same for both positive charges and negative charges. And the situation is also occurs in ionic solutions. So thank you very much.